Hello and welcome to Dare to Know, interviews with quality and reliability thought leaders. I'm Tim Rogers, and today we have a special interview recorded by Fred Schenkelberg in January 2016 at the Rams Conference in Orlando, Florida. Fred's guest was Dr. Lance Fiondella. Dr. Fiondella is an assistant professor at the Department of Electrical and Computer Engineering at the University of Massachusetts Dartmouth. He received his PhD in 2012 in computer science and engineering from the University of Connecticut. Dr. Fiondella's research interests include the reliability and risk assessment of software, systems, and networks. He has supervised 4 master's theses, and he is the advisor of 4 PhD students. Fred talked with Dr. Fiondella about his collaborations with industry on risk management issues. Let's join Fred's interview with Dr. Lance Fiondella.
So welcome to Dare to Know. This is Fred Schenkelberg, and I'm sitting down with Lance Fiondella. I'm sorry, I stumbled on that. I even tried it a couple of times, but now, we're at the Rams conference, and you probably are going to pick up some of the background stuff that's going on, because there's a lot of people here who are talking about reliability, and some of them, I suspect quite a few, came in part to see your tutorial that you do.
We did have quite an audience today, so it was a session, I would say maybe 50 attendees or so in the software reliability modeling tutorial.
Software reliability. And I thought you had math in there at one point.
Well, there was the formal title was Introduction to Mathematical Software Reliability Models.
Okay.
But again, it intended to be a basic introduction. You know, I intentionally provide as you would see in a traditional mathematics textbook, they have appendices with the laws of algebra or exponents you might need to know. So we went through that because I want to dispel the belief that this is complicated to get into.
Right.
So starting from rules of differentiation and laws of exponents and logarithms, really calculus 1 and 2 is all you need to get started, understanding the basic models and going from there into a review of some of the concepts of estimation. So given some event time data, or in the context of reliability, failure time data, how do we find a curve of best fit for a model in a mathematical sense? So,
all right. So some of that's just straight regression analysis of the different times of ways of going at it. You're dealing with a software system, so it's time to a defect found or a bug found.
Right, fault exposure.
Fault exposure like that. And it wasn't that long ago people didn't believe software had reliability concepts or stuff.
So there's a popular argument that goes around, and I'll repeat one form of it, which is software is deterministic. If you give it an input, or it will produce the same output no matter what.
That's right.
So
until you
therefore,
fire up Microsoft operating system.
But the idea being that it's either works or it doesn't, and once you fix it, it's fixed forever. Therefore, it is this binary state, 0 or 1, 1 being reliable, 0 being unreliable.
Right.
I guess the oversimplification there is that when you talk about, say, the operational profile of a software, which can be everything from the inputs, including configuration files, the sensor data that's reading something in and then feeding it to software, there is randomness in the time to exercising the code where the fault resides. So that oversimplification tends to disregard that the randomness in the environment and configuration can drive the first time to discover a fault that would then send the engineers back to the drawing board to try to do fault isolation and removal.
Okay, so we're gathering this event data or failure type data, and then you were talking about your tutorial goes after these models, and so I've done some work in the software world and things like defect density and it's a Dwayne plots or models and things like that. Is it that kind of thing, or is it? And it's been a while since I've dove into that area now, so I might have to sign up for your class or actually attend your tutorial.
All right. Well, in any case,
well, I mean, am I on the right track?
Well, yeah.
Why would I, as a reliability engineer, want to know this?
Well, it's not what I again with the review that I give at the beginning of the tutorial. I try to emphasize that even though software is this different entity, it fails in a different way. It doesn't have, you can't kick it the same way. You can kick hardware, which has a set of reliability models. There is some similarities in the mathematics. So, you'll have these models based on, you'll have the event time data, but then how do you characterize it? One popular class would be these non-homogeneous Poisson process models, which are a time
repairable system, they call them.
Right. So you see the NHPP models, but I start very simply to say let's begin from what is, we know what least squares estimation is, to find that minimized distance between the curve of best fit and the data points to minimize those vertical distances, but instead looking at another method, the maximum likelihood method, where we talk about samples from a distribution and the probable, what are the numerical values of the parameters of a model that best characterize the data that would give us that, quote, curve of best fit. So we review very simple concepts from discrete probability and continuous probability, even give an example in the context of, say, flipping a coin a certain number of times, and then from that inferring, but showing that you can go through a calculus-based procedure, simple differential calculus, to derive algebraic equations that make intuitive sense, as, say, for example, the number of successes divided by the number of coin flips would tell you the best estimate of your probability of that coin coming up heads, and also the simple exponential distribution, because one of the, what we call failure rate, or another group of researchers would like to call hazard rate, there's a class of models where there's a discrete sequence of failures, but instead of them being what we call independent and identically distributed, where every single failure, like a hardware population where we might have a set of items on test, and we're going to break 100 of them or run them until they wear out, we're talking about a piece of software that's being tested, and as faults are removed, the rate of occurrence of failure should be decreasing on average. So instead,
not in every software team.
Well, preferably. And certainly I can go through those cases too. And the reality is that processes really make things, the complexity of software these days certainly makes the classical models from decades ago harder to characterize everything, and there's certainly some good research going on in that direction.
So let's assume they're doing a good job and they're fixing things and making improvements, but it's not testing 100 iterations. It's testing one that keeps changing.
Well, right. So there are these complexities to say, well, I changed my software. Is it even the same physical or same logical item, object it was before I made that fix? But we try to do the suspension of disbelief for the time being, simply because we want to preserve mathematical tractability, and trying to get away from those some oversimplifying assumptions too quickly may introduce issues that really don't resolve. For example, cursive dimensionality. Why do I need 3 parameters when 2 would suffice? When parameter 2 times parameter 3's values could take any possible combination of values within the feasible range, does that third parameter really characterize something about that testing process or the rate of exposure of faults? So we try to avoid that. In statistics, we call it the cursive dimensionality, and preserve simplicity. Whether it's a 2-parameter model, but these failure or hazard rate models, instead of simply saying the 100, iPods I'm going to drop on the ground, or iPads, and we do our drop tests in our specialized unit. Instead, we're talking about software that has essentially the faults will have independent realizations, but they're not identical. That is, each time we remove a fault, the rate of occurrence of failure should decrease by some amount, but that rate is still exponential. So instead of having a product of IID, or independent and identically distributed faults, we have these independent but non-identical faults where the sequence is decreasing. So the mathematics becomes a little bit more complicated, but it's just indexed I from 1 to 100, lambda sub I. So you still have your lambda e to the minus lambda t forms, but now those lambdas have an index I for the ith fault. And the math goes through, and it really doesn't make it too much more complicated.
Not really.
When we're doing your logs and differentiation.
Well, you also mentioned that you've got a package, basically, an open source set of tools, basically. And didn't you go into that much in the tutorial?
Yes, right. So we gave a demo, and certainly it's good to understand the underlying mathematics. Maybe the boss only wants to see a plot to say we're on track or we're in trouble.
Right.
But it helps to know why, the underlying assumptions that are implicit within the mathematical formulations. It's important to know what is essentially baked into the equations. What are we implicitly assuming? And it's up to somebody to, if they want to propose a more general model, they have to remove those assumptions. So there's certainly value in learning the underlying mathematics to help make decisions wisely. But in this case, we've implemented a tool and populated it with a set of 5 models. These were simple models that were popular, and many of them were implemented in a previous tool which is no longer supported. That was the CASRI tool developed by Alan Nakora of Jet Propulsion Laboratory and Michael Liu, who's now at City University of Hong Kong. So they had the CASRI tool, which I'm forgetting the spelled out version of the acronym, but actually Alan, myself, we worked on the project with support from the Navy to re-engineer the tool in a way that would, it's not the quote forever solution, but hopefully it will be around for long enough that people can make good use of it. That is, it's now, instead of being closed source, it's open source. That has certain implications. One is anybody from the international research community who has a model, we have an open architecture, they can follow our contributor's guide standard and implement a model, test it against some data sets, verify that it's working, produces the plots, and then plug it into our graphical user interface.
So and then the structure for them to bring their formulas and their algorithms basically to it. Right. And so it's all in R, from my understanding.
That's right.
And it was just the popular research language now for statistics and others.
My idea was, one, keep it free, and so therefore try to implement it on top of a tool that's free.
Right.
Keep it open source, so implement it on a tool that's open source, so that it is truly free and open source, other than down to the operating system. You have to buy the computer, but the software, you're not paying licenses. We're not plugging a back end into a commercial tool that would charge a license. We want to get away from that because that certainly limits the ability of those who are resource constrained from working with the tools.
Well, it also encourages collaboration and sharing of more models, more details, you get more input in it rather than all being siloed around.
That's
which is a big point of this conference, and is to share ideas and do all that stuff.
Right. So unlike many, we all may have proposed a model of some form or another because we said, hey, I saw that data set and it looked like it followed this curve.
Right.
Well, let me work it out and see if that model, do the math out and see how well it fits compared to the others. Really, my belief is that there's been a real divergence between the academic community and the practitioners who can benefit from some of the modeling. And what I was hoping to see by developing this project was to create a kind of sandbox to promote collaboration and communication.
Okay.
What I mean by that is I'm not out to promote any model. We put 5 models into the tool just to get it started. None of those are my models. I simply want people to be able to add whatever model. I don't think I have the bandwidth. So in some sense, the open architecture is crowdsourcing the problem of going through 40 years of the research literature. If a new student is doing their master's project, they can go find a paper and say, oh, here's this classical model from famous Professor X in country Y. I'm going to do that for my project. And then go implement it and go through the contributor guide process, pass the validation test, get it inserted into the tool, and then it's available for the user community to decide whether it's any good or not.
Or if it's useful or not,
to me,
helps them.
exactly. So
perfect.
my theory is it's an efficient market. It's a kind of matchmaking environment where let the users decide what's useful and not. And in the other direction, my goal is to let the folks from industry try it out, kick the tires, say good, no good, in between, and then come back to the researchers and say, that partially addresses my problem, but I also have this kind of related problem. Can you help me solve that? And maybe it's already solved in the research literature. Maybe it goes in the tool. Maybe it goes into a complementary tool. So in essence, create that two-directional conversation to actually create a tool. I joke, I say, this tool is for the users, not for me, because many researchers will create a tool which advertises a collection of their own results as opposed to something that's for everybody, right? Everybody can contribute their models, their measures of goodness of fit, and this would in some ways also promote standardization and repeatability of research. It's no longer, I have my model, that old model that anybody can beat because, it's just, we know that the shape of the curve isn't so, flexible. So in other words, forcing a higher standard of quality when it comes to repeatability, comparability, and to have that single shared platform for the international research community. That's really one of my goals, to up the standards of research and start asking the practitioners, what do you really need from us?
So I got two follow-up questions. I mean, I know you talk about it in the tutorial, but where can people find the model and get involved with this this community, these software models?
Well, so there's certain places where they're published. Obviously, the RAMS proceedings is one place where you've seen models proposed, but there's certain popular publications. The IEEE Transactions on Reliability has.
Well, that's where we can find the models. I'm thinking about the tool you're building. And
you mean the actual where can you get the tool?
Right.
Okay, so I make it available on my website, which is it's a third-party site. So it's a registered Google domain.
And I'll get the link from you. We'll put it in the show notes.
All right, sounds good. All right, I won't spell it out.
Yeah, that's fine. We can add the link electronically to the show notes.
Absolutely.
But it's a package in R, so it's being familiar with R to some extent, and loading the package and stuff. And then I know the tutorial introduces some of the background and basics of that and demo of it. Is there other material available other than going to Dartmouth? I think that's where you're at, right? Go to Dartmouth and take your classes.
Right. So, I mean, certainly I'm hoping to get that short text written at some point, but I'm still untenured. We'll see how quickly that happens. But the website provides a set of resources. One is a web-based instance of the tool. So you can go there. You don't have to download anything. It's just a web version.
Ready to run.
Right. It's there. And not only that, there's a set of data sets taken from a very popular Handbook of Software Reliability, which was edited by Michael Liu in the 1995. It's got some very famous data sets which are prepared. It's in Excel format. So the input formats are fairly standard, hopefully across organizations, either Excel spreadsheet or comma-separated variable files. So we give these data sets all in the form ready for input into the tool. So one, you don't need to download and install the tool if you just want to get started and learn. Two, you don't have to go collect your own data. You have historical data sets you can play around with. And three, there's a user guide which has a tutorial. It'll walk you through, click here, here's what you should see, here's how you interpret it. So that set of documents and resources is to just learn. And then if it's open source, meaning you have access to the code. You can go to the GitHub repository, you can download it. If your organization has concerns with security, so again, defense-related, users might have concerns about information security. They have the source code. They can go through the information assurance procedures of their organization so that they can be confident that this doesn't have any trapdoors. It is secure. So in that regard, by providing the source code, yes, we understand there's a little bit of extra overhead, but it's, again, attempting to serve communities. Again, even commercial proprietary wants to make sure they might want to adapt it. As I say, I want to give the research away because in doing so, my hope is to get more feedback about what are the real burning issues in industry as opposed to here's more models. I don't necessarily think that's what we need.
That's right. And you mentioned that right at the start, is that gap between the academic and practical side and bridging that, making sure what you're doing is more practical. So in the campus and with your students, do you get much of the industry researchers to bring projects in or interact with that, or is this the tool and this idea one of the venues for doing that?
Well, at this point, our primary visitor list, it tends to be the local defense contractors. So they've come down, people supporting different branches of the armed services, Army, Navy, Air Force, who they might be former graduates of our program
Right.
who are now working for the local defense contracting community. Certainly, industry has expressed interest. They have a little bit more variety in terms of their processes and
Right.
development, but certainly there's
Right.
there's potential to collaborate there as well.
Okay.
So-
And there they just contact you.
yeah. I mean, I've had folks come down. I get phone calls. I've on occasion said, well, if you don't want to drive out here, it's very scenic. But if you would just like to have a phone conversation, or we do some kind of screen sharing to walk you through.
Right.
I think at some point, if the volume becomes too high, we'll probably do some videos where the students will do here's the screen and walk you
shares,
through. Yeah, and so just give the video tutorial as opposed to the written document.
That's right. That's right. Now, the way you describe the tool and the mathematics behind it, it's not specifically. I mean, you've written it for software packages and defect tracking, and not defect tracking, but modeling of future defects, and defect rates, defect density, I think is the common term. But it certainly sounds like it would work for repairable systems.
So there's certainly some relationships, but many of those NHPP, the non-homogeneous Poisson process models, typically have a model form that assumes that there's a certain finite number of faults and then a distribution on the discovery time. So it's
Right.
essentially a scaled cumulative distribution function. So
Yeah, and I've heard that analogy a number of times, but that's obviously a simplification.
Right, but at the same time, it ultimately the models. What are I think the underlying question that anybody wants to ask is, what can I use this model for?
Right.
So before I
That's a
even
good
bother
question,
learning
yeah.
before I try to study all this and figure it out,
Right.
what questions will enable me to answer? So with the failure rate or hazard rate models as they're termed, we typically can ask simple questions like, how much additional testing time would be required to achieve a desired failure rate or
Right.
intensity? Meaning, if I have a schedule to stick to and I can see that, I'm going to require so many additional weeks or months of testing, I might know I'm either on track or I'm behind schedule. So
Right.
certainly knowing the projecting whether or not I'm going to make my scheduled deadlines is certainly one. Others would be, how many faults were latent in the software,
Right.
and how many would be remaining. If I couple that with, say, only measuring certain ones of a higher criticality than a given threshold, I know how many severity level 1 or 2s I've got in there, and we can obviously manually filter the data based on severity, or roll up just the 1s and the 2s and disregards the 3, 4s, and 5s if those are lower severity,
Right.
just to know how are we doing and within certain processes you have to get to 0 on the most severe before you can, somebody's going to say, okay, let's exactly, right? And to be able to answer those kinds of questions provides guidance to say, are we doing enough? Of course, you need to be designing tests that are representative of what you want your system to do.
Right,
Remember,
right.
Reliability models are a mathematical approximation of reality. Those, many times, the software engineering community, I'm a computer scientist by training, so I have an appreciation of this, that, the software engineers, we went into programming because there was something about math that drove us to programming. It worked, it clicked. When you were successful, it was successful. It could be, it's like electroshock therapy at times, but when it works, it works. When it fails, you get a good negative feedback to say that's not how you do it correctly.
Right.
But
Right.
understanding the value of both the programming and the mathematics to use as a benchmark, it's in isolation, reliability modeling is not the answer. You need to concern yourself with the functional requirements. Does the software do what it's going to be designed to do?
That's right.
Until I check all the boxes, say yes, function 1, function 2, whatever we're developing for the customer is working, how can I say testing is done? And the test should be representative of what it needs to do, or the usage profile.
For the customer.
And certainly there's going to be some uncertainty in that, but to couple both the common sense programming, we need to make it do this, with the mathematics of here's how often it failed, to say, hey, we're getting better. At least it's less bad than it was before,
Right.
feel like we're making progress as opposed to going in the wrong direction, having reliability growth, not deterioration.
Which I think we both have witnessed a few
But
times.
it's reality with such complexity in software testing.
Right.
You have many systems that are so large, you're integrating in layers. You might have block 1 tested, and then you're testing block 2, right? After. But block 2 has been added to block 1. Now, in that first stage of testing with just block 1, you're exposing faults within block 1's code only.
Right.
But block 2 now interacts with block 1. So you're exposing faults from block 2. You're also exposing faults from block 1 and faults that interact, but across those boundaries that are now being connected.
That's right.
So this notion of integration testing and layering or block testing of very complex software systems is introducing this kind of not discontinuities, but the kinks in the curves that lead to these more complex models, what they call change point models, where you might have what looks like a stock market recovery. You have the strong up curve and one that's a little bit weaker, and a third that's
correction.
Things like, well, hopefully not that.
Not too many corrections.
But the notion that, as you're applying the tests, you're exposing faults, but then you're adding code. So there's, as I said, some more complex models that would hopefully characterize these more complex software testing and integration procedures that you see with the modern systems.
Okay. Well, I'm gonna wrap it up here and leave a note to the listeners. If you're coming to RAMS, and the way you described it, Lance, is it's building on the foundational pieces so you get the understanding. It's not enough just to have a calculator, a fancy calculator, to crank out a number for you or to grab whatever model, but use it with intelligence and understanding. And I think that's what you're introducing and talking about in the tutorial. Is that fair?
Right. And it's a conversation between all the stakeholders, and not just software engineers, customers, and everybody else.
That's right. Well, all the best to you with the software and the tool and the package and building that community. I'm going to have to touch base with you regularly and see how that's going and see how I can support you with all that. So
absolutely.
Thank
you.
Well, thank you very much, Lance. Appreciate it.
Thanks, Fred.